Okay, so you guys were tasked with doing this problem on your own yesterday. Couple parts were a little nasty, but we'll talk about them all so you know where the information came from. So part one of this question says the second ionization energy for sodium is about 3 times greater than the second ionization energy of magnesium. So a good thing to do in this case, since there's not a periodic table in front of us, is to go ahead and do the electron configuration for each of these, sodium and magnesium, just so we can kind of see where they're located on the periodic table. So we've got neon, what? Well, actually, you know what? I'm going to do the full electron configuration because we'll be able to see all the different things we're taking off. So it's 1s2, 2s2, then what? 2p, 6, 3s, 1. And then magnesium is 1s2, 2s2, 2p6, 3s2. So the question is wanting to know, how come removal of the second electron in sodium is 3 times greater than the second electron removal in magnesium? Why is that? Sodium is, that second electron in sodium is what? It's a core electron. Removal of the second electron in sodium is removing a core electron. That requires more energy. Therefore, the ionization energy is higher. Got it? That should have been a pretty easy one for you. Now this next one, the difference between the atomic radii of sodium and potassium is relatively large compared to the difference between the atomic radii of rubidium and cesium. This is a pretty nasty question, but I just wanted you to sit with it for a while and see if you could come up with this. I believe you talked about electrons. Did you show them the Balmer series and the difference? So I'm thinking you've seen this. You just might not have remembered at the time when you were doing this last night. But as you go from sodium to potassium, what energy levels are we dealing with here? 3 to 4. And if we go from rubidium to cesium, we're going from 5 to 6. On the next slide, I've just inserted this for you to see. If you haven't, if you recognize, does anyone recognize kind of what this looks like? As levels get further and further away from the nucleus, they get closer and closer together. All right? So we were comparing 3 to 2 to 5 to 4. And just by looking at the level of energy, that's indicative to distance, because the further away, the less energy, right? So that explains it right there. This is just the full spectrum of hydrogen. Lyman, Ballman, and Paskin are just the different types of light that would come up. This, I believe, is like UV light. This is visible. I think this is IR. The name for this full picture is just, I looked up hydrogen spectrum when I was looking for it. So will they test you on something like that? Probably not. I haven't seen it on the AP period. In many, many of all the tests I've looked at, I haven't seen it. So you can just write, as you get further from the nucleus, energy levels get closer together. All right, part C I definitely expect you to be able to do. Part C was a sample of nickel chloride is attracted into a magnetic field, whereas a sample of solid zinc chloride is not. Why is that? There's only, I brought this up. What do y'all think? Which one's paramagnetic? The nickel is. So as far as how to answer this on the AP, you can't just say it's paramagnetic, because the definition of paramagnetic is being attracted to a magnetic field. I graded a question just like this. And what's making it paramagnetic? That's what you need to say. What is making something paramagnetic? Unpaired electrons. So you have to indicate that nickel has unpaired electrons. And the best way to do that is to go ahead and do your spin diagram or your electron configuration. I would do kind of both. I would go AR 4s2. What's nickel? 3D. You guys can see the chart. I can't. 3D. 3D 8. And then zinc is 4s2 3D 10. So if you look at this right here, these were in a spin diagram, you could see you would have unpaired electrons. So you would say nickel is attracted to a magnetic field because it has unpaired electrons. It is not sufficient to say it's paramagnetic. All right, Part D, we're going to cover more when we get to bonding, but it's one that I'm fairly certain that some of you probably figured out. The question is, why does P have the capability of making PF3 and PF5 while nitrogen can only do NF3? What does it mean to be able to go ahead and attach 5 things to your central atom? Any ideas? If you have 5 things attached to the central atom, you have to have an expanded octet, because normally the normal valence maximum is 8 electrons. So this P has the capability of expanding its octet. Nitrogen, because that's the only thing it can make there, obviously does not have that capability. The question is why? And you did this in pre-AP. No. Where do electrons and valence electrons come from normally? Where do those 8 electrons, what orbital types do they come from? S and Ps. Because there's a capability of d orbitals on energy level 3 and beyond, things on level 3 are capable of expanding their octet. That's the answer. Atoms on the 3rd level and beyond are capable of expanding their octet. All right, so that's that question. Let's move on to some math here. This is going to be solid review for the test. You should be capable of doing all these math problems. It says the longest wavelength of light with enough energy to break a Cl-Cl bond in Cl2. So this is basically the energy required to break the bond in one molecule. The wavelength required to break the bond in one molecule is 495 nanometers. The first part says to calculate the frequency of this light. So what equation can we calculate frequency if we know wavelength? C is equal to, speed of light is equal to wavelength times frequency. So we're going to go ahead and plug our information in. 3.0 times 10 to the 8th meters per second is equal to, we have an issue though. What's wrong? We need meters, so we're going to do a conversion. For every 1 meter, I have 1 times 10 to the 9th nanometers. So that's my wavelength, and I'm going to solve for frequency. When I solve for this frequency, I get an answer of 6.06 times 10 to the 14th per second. Question. Next, calculate the energy in joules of the photon of this light. How can I calculate energy in joules now that I know frequency? There's a short version. You can do E equals hc over lambda. That's kind of long. There's an either E equals hv. Exactly. So I'm going to figure for this one, energy is equal to Planck's constant times the frequency. So I'm calculating energy. Planck's constant is 6.63 times 10 to the negative 34th joule seconds. We're going to multiply that by the frequency from the previous problem of 6.06 times 10 to the 14th per second, giving me a final answer of 4.02 times 10 to the negative 19th joules. The final part of this says, calculate the minimum energy then in kilojoules per mole. Well, that's joules, but it's joules of what? One molecule. So that's really joules per molecule. We need to convert that to kilojoules per mole. So I'm going to start out, dimensional analysis is our friend. 4.02 times 10 to the negative 19th joules per molecule. So what do you want to convert first? Joules to kilojoules. So for every 1 kilojoule, I have 1,000 joules. And then, how do I get to moles? Well, for every 1 mole on the bottom, there are 6.02 times 10 to the 23rd. And when you see this answer, you're going to realize why we like it in this unit. Because when you do it, you end up getting an answer of 242 kilojoules per mole. That's a little bit easier number to deal with than 4.02 times 10 to the negative 19th. Okay. Next part. A certain line in the spectrum of atomic hydrogen is associated with the electronic transition in the hydrogen atom from the 6th energy level to the 2nd energy level. Indicate whether the H atom emits or whether it absorbs energy during this transition. We're going from 6 to 2. Emits or absorbs? Emits. When electrons fall, they emit. Why? Because they're being pulled toward the nucleus, right? That's something that's probably going to happen pretty naturally as opposed to moving against the positive charge of the nucleus and going up to higher energy levels. All right. Now we have to calculate the wavelength in nanometers of the radiation associated with that transition. So since this is hydrogen, we can actually use an equation to find that, and that was called, remember, Rydberg? The Rydberg equation. We're going to use the one on the AP equation sheet where we take final minus initial. So we're going to do energy 2 minus energy 6. So to set that up, we're going to use the little thing that they had. It was, someone looked that up. What was it was negative 1.2 or negative, I thought I had this written down. Oh, there it is. Negative 2.17 times 10 to the negative 18th. And this is on your AP equation sheet. Don't memorize it. Obviously, I don't have it memorized. Final minus initial. So what was the final state? 2, and we square it, minus negative 2.17 times 10 to the negative 18th, an initial 6 squared. When you do that math, you end up getting an energy of negative 4.18 E negative 19, and this is in joules. It makes sense that it's negative because it's going from level 6 to 2, so it has to be negative because it's emitting that energy. So this is 4.0882. 4.82 times 10 to the negative 19th. All right, that's energy. But they didn't want energy. What do they want from us? Wavelength in nanometers. So what we're going to do, and I'm going to let people at home do it on their own. I'll give you how to do it, and I'll give you the answer. But we're going to take this and plug it into E equals hc over lambda. We're going to take that energy, plug it in here, and we're going to put in Planck's constant and the speed of light and solve for wavelength. What unit is that wavelength going to come out in? Meters. And then we have to convert that to nanometers. People at home, press pause and do this on your own, and I will write the answer up. The answer turns out, after all the work, to be 411 nanometers. I really like this last question because it makes people think a little bit. This last part asks, okay, we know this happens in a hydrogen atom, but what would be the difference or the energy, difference in energy associated with the transition from 6 to 2 in a helium plus ion? What's the difference between a helium plus atom and a hydrogen atom? More protons. What about the electrons? Same number of electrons, so they're isoelectronic, but He plus has more protons. So tell me about that electron going from level 6 to 2. Yeah, it's going to come down with more energy. Why? There's more nuclear pull on that particular, from that nucleus to that particular electron. There's more nuclear pull because the nucleus has got more protons. It would be like if gravity on the Earth was 12 point whatever, not 9.8, right? And in doing that, if we fell off a building, we'd probably fall with a little more intensity. Okay? More nuclear pull. And then it would be opposite if that electron were trying to go up a level. It would require more energy because the pull is greater. So the energy then would be greater. Greater energy associated with that transition because there's more nuclear pull. All right, next problem is to write the ground state electron configuration for an arsenic atom showing the number of electrons in each subshell. Since they're saying in each subshell, that's going to pretty much require that you write the full electron configuration. They're saying basically you are not allowed to do core. So let's do it. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p what? 4p3. Done. Part B says, give one permissible set of 4 quantum numbers for each of the outermost electrons. So what is that? What are we finding the quantum numbers for? Valence electrons. How many valence electrons? You really don't even need a periodic table to answer this question because this electron configuration gives you everything you need. There's 5, exactly. You've got these 2 and those 3 electrons. So we have 5 sets of quantum numbers to write. We got to get busy on that. So let's start with these S's. First quantum number, 4. It's an S. 0, 0, plus 1/2. The next S is 4, 0, 0, minus 1/2. Now let's look at our P's. Still level 4, 1, minus 1, plus 1/2. Now, remember Hund's rule, we go into the next orbital, 4, 1, 0, plus 1/2. And the last one, 4, 1, 1, plus 1/2. Done. C. Is an associated arsenic atom in the ground state paramagnetic or diamagnetic? Well, we have the electron configuration done. Looking here, what does that look like? How are those electrons placed in that p sublevel? Up, up, up. So we have unpaired electrons. Whoops, unpaired. So therefore it's paramagnetic. I don't know where D went. E. Explain how the electron configuration of the arsenic atom in the ground state is consistent with the existence of the following compounds. So when we look at, all I really need to look at to talk about bonding is stuff beyond the noble gas configuration. We don't ever need to look at all of this stuff here. So I'm just going to go ahead and stick with argon, 4s2, 3d10, and 4p3. So in our first question, they're asking about Na3As. If you notice, that's an ionic compound. In ionic bonding, and we're going to cover this more next unit, electrons are totally transferred. So sodium is going to become +1, and arsenic is going to become, what? -3. So it's going to grab an electron from every one of those 3 sodiums in this compound. The question that I have for you is, where is it going to put them? Where can arsenic get its electrons? Where is it going to put them? Right here. Remember, currently, that's what the P situation is, right? So can't we put 3 electrons from sodiums there? Okay, and at that point now, this becomes a -3, and it can ionically bond with 3 sodium pluses. Okay, that's that justification. Now let's look at the next one. We're looking at AsCl3. This is a little bit different because this bonding is not ionic. This is covalent bonding. And in covalent bonding, electrons are thrown in the mix and we get hybrid orbitals and all that stuff. But we do know that each chlorine to be a full octet needs how many electrons? To have a full octet, it needs 8. But what does it need from chlorine to become full? It needs 1 electron. Well, there's 3 of them, so how many electrons does arsenic need to donate to the pool? So arsenic needs to donate 3. We usually donate from our valence shell. Which electrons is it going to donate? Again, it's going to donate those. Okay, so we're going to get our 4p3 is where the electrons are going to come from that arsenic's going to throw into the mix. Why can arsenic make AsCl5 then? How many electrons would arsenic need to donate to the pool to please our friend chlorine there? 5 of them. So arsenic needs to donate 5. Where is it going to get that 5? Here and here. So from its 4p3 and its 4s2, those are the electrons arsenic will use to do what it needs to do. Got it? All right, last problem. You know, I'm going to go real quick over this because this is exactly what we did yesterday, and I want you guys to handle this, but this is a really, really typical type of question. The first part says, in general, there's an increase in ionization energy from Li to Na, and that you're supposed to explain it. So in this graph, they've just graphed the ionization energies all the way across level 2. So the question is, why the general trend? As you go across the table, the effective what? Increases. Therefore, I'm just going to write nuclear pull as well, increases, or effective nuclear charge increases. You can say any of that. And it gets harder and harder to remove an electron. Those atoms get smaller and smaller, so it's harder and harder to remove. So therefore, that's an increase in ionization energy. And that's why the trend is upwards. Part B. The first ionization energy of boron is lower than that of beryllium. This is our first exception. The last electron in boron is in what type of orbital? A p orbital. Due to the shape and proximity of that orbital from the nucleus, it's a bit easier to remove that electron. Therefore, that's a lower ionization energy. Part C, the first ionization energy of O is lower than that of N, so that is our next exception. The last electron in O, what is it experiencing? Repulsive forces, making it easier to remove. Or making it less stable. Therefore, lower ionization energy. And our last one, Part D, predict how the first ionization energy of Na compares to those of Li and Ne. Well, we can kind of rank them. If we rank them, that would help. We know of the three of them, what has the least ionization energy? What? Na? Huh? Oh, you're right. I was thinking hardest. So take it back. So what's the easiest? You were right, Na. And then what's next? Li, and then Ne. Ne is the smallest of all three of those, so it's going to have the highest first ionization energy. So predict how the first ionization energy compares. Na has the lowest of all three because it's on the third energy level. I should say the last electron, not the actual atom. The last electron in Na has the lowest of all three because it's on the third energy level. Other electrons are on second and experience less shielding. All right, there are lots of ways to answer these. It's going to be important for you guys to practice, rehearse how you might answer all those exceptions along with all the trends, being able to verbally explain them. You guys can start in preparation for your quiz tomorrow. In the folder, the Unit 6 folder, it says more problems to practice for review, and that's a bunch of multiple choice questions. There's not any free response like this, but at least you can practice the content. All right? Done.